Introducing aPriori.
Hello, everyone, and thank you for joining me for the 2022 aPriori Manufacturing Insights Conference. Today, we are going to go over one of our newest cost models, sheet metal roll forming. My name is James Diedish, and I'm an application engineer at aPriori. Today, I'll be presenting an overview of our roll forming cost model, highlighting some of typical uses and advantages of this process. First off, we're going to go over a process overview of roll forming. I'll go into a live demonstration, followed by some question and answer, and the conclusion. Sheet metal roll forming is a high-speed method of progressively bending coiled metal into a uniform cross-section through a series of roller dies. So some of the benefits of this include, when you start getting into high production volumes, you're able to do this with a wide range of metallic materials. It typically has a pretty low scrap rate. You can achieve some pretty close tolerances with roll forming. It has a very superior surface finish, so for Class A surfaces, you get a really long tool life out of roll forming. You're able to produce extremely long parts, and this is a way to reduce cost and weight in certain situations. Now, some sample applications of where you see roll forming in everyday life is a lot in the automotive and transportation industry. Think of, a pickup truck box. The rails are typically made with roll forming and then welded together. You see roll forming in a lot of consumer products, in the aerospace industry, even in green energy applications like these solar panels. Some really common applications are, crash barriers you see along the side of the roads, and even metal roofs are all made with roll forming. So with sheet metal roll forming, when we were creating a cost model at aPriori, we have to go through a comprehensive evaluation of all of the process steps and alternative methods. So what we're showing below is kind of a typical situation where we start with an uncoiler. The material runs through a flattener. In this case, if the tolerances allow it, we will punch the holes in a pre-punch press, and then the material will then enter into the entry guide and go through the progressive roll forming mills, the dies that are kind of shaping the material. It'll go through a straightener and curving unit, and then it may go in through a seam welder, and then there'll be a cutoff press, and we've got a couple of different methods for cutting off, and then finally, delivering it to the runoff table. Some things you want to take into consideration is that cycle time and process cost is determined by the achievable line speed of the slowest process in the line. The tool costs are determined by the number or size of the rolls and the roller material, plus any extra tooling for punching and cutoff presses. Material utilization considers holes and cutouts, and if you're using certain cutoff methods, if it produces a slug, we take that into our material utilization calculation. When we get into the live demo, I'll explain this chart a little bit more. But essentially what I did is leveraged aPriori's strengths through matrix costing. And so I took this part that we're going to demo and I ran it through an escalating volume condition starting at 100 parts per year to 200 and just doubled until I got to about 1 million parts. And so I did this method using sheet metal and then sheet metal roll forming. And so as the volume of sheet metal went up, it starts with, no tooling, low cost brake press methods. And then once the volumes justify it, it starts getting into some tooled operations. And then all the way up to full progressive die stamping situations. And with roll forming, the investment up front is going to be very high at low volumes, and so your piece part cost is going to be very high in a fully burdened state until you start hitting, higher volumes. And then what I'm showing here is when I compare them with the two different processes, you start seeing a break-even point on the investment side at about 50,000 parts versus a conventional sheet metal approach. So let's go ahead and transition into our live demo. So here we are in aPriori Professional. I've selected in our process groups the sheet metal roll forming. I'm going to use our aPriori USA Digital Factory. We're going to use a cold worked 1020 steel, and we're going to operate at a volume of 12,000 parts. So I'll go ahead and analyze this part and come up with my result. Let's go ahead and start investigating the geometry of the roll forming process. So if I click on components, I can go into my blank, and what you're going to see on the screen is aPriori is going to unfold the roll forming process into its flat, shape that it comes off of the coil. I can also go ahead and click on the cross section, and it's going to show me here in the corner what the end shape is going to be. It's going to tell me what the up direction is and where direction it's coming from. Let's go ahead and zoom in on the cross section right here. So aPriori determines an orientation that will maximize the accessibility of the bends and minimize tooling size and complexity. And the goal being to generally balance the cross section from left to right to enable geometry on each side of the cross section to be made simultaneously, minimizing the number of passes. Now let's go into my geometric cross drivers and open up my bending and forming and click on the bend node. When I do that, I'm going to highlight the part features that get made by the roll forming mill. I see that all these straight bend GCDs are orthogonal to the cross section and running the length of the part, which are created by passing through a series of roll dies. If the whole part were bent along the length after the profile was formed, we recognize that as a bend GCD and not a straight bend GCD. So all of these are straight bends. So we can differentiate between bends made by the roll forming mill, which you see here, and then forms that are made subsequently maybe by a roll bending operation or some other forming or bending operation. Next, let's take a look at the holes. So when I click on the complex holes GCD, note that any cuts through the material will be recognized either as complex holes for any non-round internal cutouts like these square cutouts, or simple holes if they are round, or cutout GCDs if they're notches which intersect with the blank edge rather than being an enclosed internal cutout. Now let's take a look at the process routing that aPriori has determined in the manufacturing process tree. So if I expand out, I see that I have a roll forming routing with roll forming coil, a coil mass material stock, an uncoiler, coil flattener, and you'll see because I have the holes, the complex holes selected in my geometric cost drivers, it also highlights that these were created using a punching step. So just like the slide I showed earlier, we start with a coil of material stock, cut to the width of the part's flattened blank, which we showed in the GCDs earlier. We then have an uncoiler process to feed this into the line, a coil flattener or straightener, which is used to correct crossbow in thicker gauge materials and longitudinal bow in higher strength materials, and to prepare for any pre-punching operations. A pre-punch press, which performs all the punching of the holes and cutouts that can be done in the flattened state. Next, we have our roll forming mill, of course, which we've determined will include 12 passes. So if I open up my roll forming, you can see that I have 12 different stations. So let's switch over to our part details to get a look at how aPriori is starting to calculate some of these things. Since roll forming involved a continuous coil-fed line, the slowest process in the routing limits the overall line speed. We display some outputs that indicate the effective line speed in which process it determines it. Here we see that the initial cost estimate we've determined that while roll forming mill could support a line speed of 1,000 millimeters per second or 1 meter per second, the cutoff press isn't capable of supporting those speeds and is the limiting factor. As a result, the line needs to be run at an operating speed of 399.53 millimeters per second. And the operating cycle time per part is 1.53 seconds. The effective line speed is slower, though, at 223.64 millimeters per second, and the effective cycle time is 2.73 seconds. If we look at the part summary tab, we'll see that the piece part cost is $10.05, and the tooling contributes to another 72 cents. The material cost makes up about 80% of the total part cost. Tooling cost is about 6.7%, setup costs about 1.1%, and the labor and overhead costs are less than 1%, so pretty low. So let's look more at this part to understand how aPriori is generating the estimates. First, I want to talk about our roll forming logic, since that's at the heart of this new cost model. You'll see we group different bends and assign them to different roll stations. So if I go ahead and click roll station 1, I highlight the associated GCDs, you can see which bends are associated to that particular roll station. If I look at which bends are made on the first roll station, I see it's these 4 bends which comprise this stiffening rib down the center of the part, plus the nearest bend on either side, which fold the wings upward. It makes sense that the rib feature is formed first, as we need to draw the material inward toward the center of the part, and the wings can be made more or less at the same time. And because those each are 90-degree bends, that geometry isn't made with just one roll die, but actually a series of 6 roll dies, each bending the material about 15 degrees until you reach the final angle. So that's why all these first 6 roll stations are highlighted. The selected bends are made incrementally over those 6 stations. So now let's move on to the 7th roll station. At this point, we begin forming other geometry in the part. These 2 pairs of outermost bends on each side of the part are formed next. We have bend group logic, which identifies bends that are close enough together that they would be formed simultaneously. You can see it takes 5 roll stations to form those, as they are 70-degree bends, not 90-degree bends. Finally, we have an idle roll station. This is a finishing pass. No additional forming occurs here, so no GCDs are assigned to it. The number of these finishing roll stations depends on the tolerance requirements for the cross-section profile. By default, aPriori assumes a standard tolerance, which requires a single finishing pass. Let's scroll back up to the punch press. So if I open up punching, expand punching press, and get to my die station, go ahead and highlight the associated GCDs, and we can see all the holes on the screen. Now let's look at how these holes are made. They're all assigned to a pre-punching process by default, meaning these holes are all punched in the flat state before going into the strip passes into the roll forming mill. If no tolerance is specified for holes and cutouts, aPriori assumes a standard tolerance requirement of plus or minus 30 thousandths of an inch, or just over 3/4 of a millimeter. which is achievable by pre-punching. You can change this assumption using the process setup option inline punching feature tolerance on the roll forming routing node. If your hole tolerance requirements are tighter, this will require a mid-punching or post-punching process, which is after the profile has been partially or fully formed. I can either specify a tighter tolerance level for all the holes using the process setup option, or I can set tolerance for an individual hole GCD. So let's go and grab complex hole number 1, and we'll put in a coordinate tolerance of 0.5 millimeter. You'll see that I'm now out of date. So let's go ahead and recost the part. So you might see that I went from having one punching station to now 2 punching stations. And so I've got a punch press for die station 2 for a post-punching operation. You should also note that while pre-punching typically is performed with a stationary die, post-forming punch dies and the cutoff die need to be accelerated, so they are moving at the line speed when they contact the part. We calculate what types of speeds are achievable given the mass of the punching and cutoff dies and the distance they have to accelerate, which is the length of the part. The achievable die speed may limit the overall line speed. So in this case, once we increased the hole tolerance and added the post-punching press into the line, it also affected the line speed. We've determined the accelerated die necessary for post-punching can only achieve a line speed of 220 millimeters per second, given the length of this part. So the operating line speed of the whole line is now 220 millimeters instead of 399 millimeters per second when the cutoff press was the speed limiting process. And the operating cycle time has increased from 1.53 seconds to 2.76 seconds, along with the batch setup time increasing due to the addition of the second punch press. Let's scroll down to our cutoff press, highlight our associated GCDs, and we see that by default we have a scissor cutoff. aPriori provides 2 options for the type of cutoff die: a scissor style cutoff die, which does not produce a slug, and a blade die that does produce a slug. aPriori will assign a scissor style die when it is feasible. Blade dies are assigned when part and cross-section geometry requires it, such as parts with cutouts on the leading or trailing edges, parts with hem bends, and parts where cross-section bends are obscured and can't be adequately supported to prevent crushing. When a blade die is selected, the material utilization calculation accounts for the scrap it produces. Let's go into our process setup options, and we can go into our cutoff operation type, and you can see its default is scissor. If we go ahead and switch this to blade, click OK. Let's go back over to our part summary, and we see that our material utilization was at 95%. We'll go ahead and recost this. And you'll see that when I switch to a slug cutoff method, we've reduced our material utilization from 95 to 94%. Finally, let's take a look at tooling estimates. We have tooling details listed in the investment tab, but most detailed view is in our tooling spreadsheet report. We estimate the cost of the roll sets based on the number of rolls, the size of the rolls estimated from the part geometry, and the tooling material, which is AISI 4140 steel by default. We also provide detailed breakdowns of the tooling for the punch press and cutoff press, similar to what we do in other sheet metal process groups. So if we go ahead and run our tooling report, When we generate our watch point report, you can see that our assumptions, match up with the process setup options from the part. The number of roll station quantity matches at 12, and the per roll station cost is broken down individually at about $1,700. Here you can see what goes into the cutoff press, the total material costs, as well as the punch press and post-punch press costs. Our roll forming cost model also supports some processes that aren't needed for this part, but will be applied for other part types. Specifically, if I go into the process setup options for roll forming coil, you can see, in the same area where I selected blade for my cutoff operation, I can also use integrated welding processes, whether they're laser welding, rotary spot welding, or integrated TIG, or none at all. Finally, I'd like to switch gears and move over to AP Analytics to show some of the benefits of how aPriori can analyze this part using matrix costing to show when it makes sense to start investing in, a high-speed process like roll forming versus building this conventionally at lower volumes. So if I go over to my AP Analytics session, as I scroll over through the data, you'll see I started out with a volume of 100, and I'm returning back a fully burdened cost of $10.09 using conventional sheet metal processes. As my volume doubles, the cost of my sheet metal part starts to go down. As the volume goes up even farther, my cost continues to go down. Here, all of a sudden, I introduce a volume of 100 parts for a roll forming process, and my piece part cost goes up to $108 per part because I've got a capital investment now requirement of $43,000. But as I start going down and I start doubling the volume, it starts making the cost of the individual piece go down rapidly until I scroll all the way to about 50,000 parts, and it starts making more sense. My fully burdened cost is reduced to $3.78, and it's about flatline to here. We're not going to really get significant piece part cost savings for our investment, but you can see as the volume goes up for sheet metal, I start having to invest in higher cost tooling in order to achieve the same sort of part volume. So it makes roll forming just that much more attractive. Thank you for joining me to learn more about the new sheet metal roll forming module. Enjoy the rest of your conference.
aPriori, making profitability and sustainability a reality for a better world.